In this segment, we will introduce the notions of multi-feature graph signals and pooling. We know that the GNN, which is a cascade of layers, each of which applies a graph convolution followed by a pointwise nonlinearity, acts on a graph signal as input. We also know that a graph signal describes data by assigning a single scalar to each node. This fact limits the descriptive power of graph signals when characterizing graph data. We will define multi-feature graph signals, which assign vectors to each node instead of a single scalar. We will thus need to adapt the graph convolution operation to handle these signals, and we will show that the resulting operation is equivalent to the application of a bank of graph filters. We will also note that using multi-feature graph signals to increase descriptive power actually increases the computational cost. Thus, we will develop pooling strategies to tackle this issue. A graph signal assigns a single scalar to each node. We see in the example here that each node supports a different signal value. We conveniently describe this signal value as a scalar and concatenate all these scalars, one for each node, on a vector x. Describing network data by assigning a single scalar to each node is certainly a limited description. We can extend this descriptive power by assigning a vector to each node instead of a scalar. For instance, when we associate a vector of dimension 2, now the graph signal becomes a matrix big X, where each column represents a scalar graph signal. We can keep adding entries to the vector associated to each node, which amounts to adding columns to the matrix big X. Each entry of the vector associated to a node is called a feature. This is how we define a multiple feature graph signal as a matrix X of size n, the number of nodes, times f, the number of features. It is important to know that row I of this matrix collects all f features at node I, and that this represents the information available at that node that can be accessed with no need of neighborhood exchanges. Column f, on the other hand, represents feature f collected across all nodes. This implies that each column x superscript f is a scalar graph signal, the same ones that we have been manipulating so far. The key operation of graph signal processing in general and GNNs in particular is that of graph convolutions. Now, we need to extend this operation to handle multi-feature signals. The convolution has to be a linear operation that depends on local information accessible only by means of neighboring exchanges, and that has a distributed implementation. The convolution operation acting on multi-feature graph signals is the one shown in the equation. To see why this is the case, let's analyze it step by step. Let's start with S times X. We have X, which is our multi-feature graph signal, where each column is a scalar graph signal representing each feature. And we have S, which is the matrix representing the sparsity pattern of the graph. For example, the adjacency matrix or the Laplacian matrix. We see that the multiplication of X by S on the left is actually shifting each graph signal feature. We are taking each row of S and using its entries to compute a linear combination with the entries in each column of X. Since each column of X is the scalar graph signal representing each feature, and since each row of S respects the sparsity of the graph, what we are actually doing is a linear combination of the values of each feature in neighboring nodes. So we are indeed shifting each of the columns as S times X to the F indicates. Now let's add matrix H. This is a matrix that replaces the scalar filter tabs that we used to use in graph convolutions. When we multiply X by H on the right, we see that we are doing a linear combination of features at each node. That is, we take each row of matrix X, which corresponds to all F features at each of the nodes, and do a linear combination of them with the entries of the filter tab in each of the columns. Note that when we multiply by a matrix on the right, we are doing linear operations that do not involve neighbor exchanges. They are computed internally by each node. So now we see that this operation is, in fact, the appropriate convolution operation for dealing with multi-feature graph signals. But how does it relate to the convolution that we were using for scalar graph signals? Well, this convolution operation is equivalent to the application of a bank of graph filters. Essentially, for each feature xf, we apply the fg filter to obtain xfg. What we mean is that we take the fg entry of matrix hk, that give us the filter type hkfg, and we filter the signal xf with this filter. This is a linear, local, and distributed operation. In fact, this is precisely the convolution that we introduced at the beginning of the tutorial. Filtering the signal f with filter fg gives us another graph signal that we denote xfg. In short, we are applying g filter to each input xf, so that we have is a filter bank with a total of f times g filters, and this is precisely the size of hk. Once we collect all these f times g graph signals, we aggregate the output of each g filter across all f features, yielding a multi-feature graph signal of precisely g features. In summary, a graph convolution on a multi-feature signal is a linear, local, and distributed operation that maps signals with f features into signals with g features. This operation is equivalent to the application of a bank of graph filters. Now that we have defined multi-feature signals and the convolution operation that works with them, we need to elaborate on how to fit this into the GNN framework. We know that a single feature GNN is defined as a concatenation of layers, each of which applies a graph convolution followed by a pointwise nonlinearity. XL becomes the graph signal at layer L, and since it is a single feature, it is a vector of size n. HLK is the kth filter type at layer L and is a scalar. The collection calligraphic H of filter types defines the parameters to learn. S is the shift operator, which is an n times n matrix that is given by the specific problem formulation. When working with GNNs, we have hyperparameters that are design choices. In a single feature GNN, these are big L, the number of layers, and big K sub L, the number of filter types on each layer. When we move to multi-feature signals, what we do is replace the convolution by the new operation we discussed on the previous slide. We see that the multi-feature GNN is virtually the same, except now big XL is a matrix of size n times FL, where FL is the number of features at layer L. HLK is no longer a scalar but a matrix of size FL-1 times FL that maps the number of features in one layer to the number of features in the next layer. The collection calligraphic H of all these matrices is now the one that contains the parameters to learn. Note that the number of parameters to learn is still independent of the size of the graph, big N. The design hyperparameters have now become the number of layers and the number of filter types on each layer as before, but we also need to decide on the number of features that we want to have on each layer. From now on, we will just refer to graph signals and graph convolutions without explicit mention of whether they are single feature or multi-feature. The thing is that increasing the number of features in each layer is actually increasing the dimension of the signal and thus increasing the computational cost of the convolution operation. To address this issue, we typically use the operation of pooling. Pooling is typically applied after the nonlinearity of each layer, and what it does, it is to construct regional summaries of information at each layer. Then it keeps only some of these regional summaries, reducing the dimensions of XL to be NL times FL for some decreasing value NL that will become a design choice. To address pooling in a graph signal processing context, we need to think of it as a local summarizing function followed by downsampling. In this equation, the pooling operator PL has become a summarizing function ρL followed by a binary selection matrix CL. The local summarizing function ρ essentially considers the values of the signal in neighboring nodes and applies a summarizing function, for instance a maximum operator, updating its value with that maximum value. We do this for all the nodes in the graph. We collect neighboring values and update the resulting node value with the maximum of the neighbor. Once we updated all signal values, we move on to downsampling. We select some of the nodes, marked here with a blue border, and keep only the values of the signal at those nodes. We do this by multiplying the graph signal with a matrix CL that maps the 11 nodes in the original graph signal to the 3 nodes selected. In short, pooling is about constructing local summaries of information and keeping only some of those summaries. Now, the thing is that the graph convolution depends on the shift operator, which is an n times n matrix that respects the size of the graph. But after pooling, the dimension of the signal x L-1 has been reduced to some number n L-1 that is certainly less than n. So a dimension mismatch arises between the shift operator s, which is of size n times n, and the signal x L-1, which is of size n L-1. To resolve this dimension mismatch, we pull a good old trick from the signal processing valve. We use zero padding. That is, we use the same sampling matrix CL-1 to adapt dimensions from NL-1 back to n. In fact, we see that CL-1 transpose multiplied with XL-1 has now size n, and that the unsampled nodes have now a zero value. That is, they have been zero padded. But this means that now the output YL has dimension n, so we kind of lose what we gained by pooling. What we need to do is to downsample it again to have size NL-1. So we multiply with CL-1, getting a signal with the same size as the input XL-1, but with FL features instead of FL-1 after being filtered at layer L. I know. Have we actually reduced the computational operation? I mean, the whole point of pooling was to reduce the computational complexity of the convolution operation. Well, if we're going to compute this operation centrally at a single computer, we just need to reduce the dimensions of the matrix multiplications involved. And we see that CL-1 multiplied by S to the K multiplied by CL-1 transpose is actually of dimension NL-1 times NL-1, which is less than n times n. Thus, we have indeed reduced the dimension of the shift operator by computing on NL-1 instead of n. Also, note that this reduced kth shift operator can be obtained before training since it depends on known quantities. If we care about decentralized computation, on the other hand, we recall that CL-1 transpose times XL-1 is a graph signal the size of the graph, with zeros in unsampled nodes. This means that multiplication with a shift operator is actually a local and distributed operation, and that it needs to be computed only at the nodes that will be later sampled. Thus, such a pooling operation not only reduces computational cost for a centralized computation, but also respects the topology of the graph for a decentralized computation.